Now let's take a look at the reaction of carboxylic acids, where carboxylic acids will be the study material on the left side of the reaction. The first one and the most important reaction is an acid-base reaction. Carboxylic acids are acids, so they can react with a base to form carboxylates. For example, benzoic acid can react with sodium bicarbonate, and it gives benzoate and carbonic acid. Carbonic acid can be decomposed to carbon dioxide and water. Okay? And I believe you've seen this reaction before in the lab. Alright, the next one, a carboxylic acid reacting with sodium hydroxide. It's going to give the carboxylate. Okay, this should be a very straightforward. And in the exam, you should not think too much about this type of reaction. Okay, it's a very simple acid-base reaction. The second reaction for carboxylic acid will be reductions. The first reduction we will look at is the reduction to primary alcohols. And we've learned this before. Carboxylic acids can be reduced to primary alcohols, but we need a very strong reducing agent, such as lithium aluminum hydride. And we typically will need excess lithium aluminum hydride because the first equivalent of hydride will react with the acid in the acid-base reaction. Hydrides are bases, okay? And we need excess hydride to reduce the carboxyl group. Sodium borohydride does not reduce carboxylic acid because sodium borohydride is a relatively weak reducing agent. Okay, the next reduction reaction is the reduction of carboxylic acids to aldehydes. Okay, we have two ways to convert carboxylic acid to aldehyde. First, we can reduce the acid with lithium aluminum hydride to primary alcohols, then oxidize primary alcohols to aldehyde with PCC. And the second, we can reduce the carboxylic acid directly with diol to aldehyde. And the diol is a modified reducing agent. It's relatively weak compared to lithium aluminum hydride. It cannot reduce aldehyde to alcohol. And here is the structure for diol. Diisobutyl aluminum hydride. Alright. Next reaction for carboxylic acid is the conversion to the acyl derivatives. In the next chapter, we will focus on the acyl derivatives. Here, I just want to mention two of them. One is acyl chloride. So when a carboxylic acid is reacting with thionyl chloride, SOCl2, it will form an acyl chloride. So now we are replacing the OH in the acid to Cl. This is a substitution reaction. We call it an nucleophilic acyl substitution. That's one of the major reaction we will focus on in the next chapter. The second acyl derivative we will look at will be esters. Carboxylic acid can be converted to esters when it's reacting with alcohols under acidic condition. And this is called the acid-catalyzed esterification. It's also called the Fischer esterification. And the Fischer esterification is also a nucleophilic acyl substitution reaction. The OH group in a carboxylic acid is replaced by the OR group from an alcohol. Now let's take a look at the mechanism. The first step is protonation. Okay, under acidic condition, the carbonyl oxygen will be protonated by the acid. Once it's protonated, the carbonyl is activated. So the alcohol, which will serve as the nucleophile, will attack on the carbonyl carbon, breaking the CO double bond. This step will form a tetrahedron intermediate. And after a proton transfer, now we have a positively charged OH group. The next step, the electrons on the unprotonated OH group will come back to reform the CO double bond, and then water will serve as the leaving group. So it will give a protonated ester as the final product. And after deprotonation, ester is the final product. Something I want to remind you here, all the steps in the mechanism are under equilibrium. All the steps are reversible. Okay, so going from acid to ester, that's the esterification. We can also go back from ester, the final product, to carboxylic acid. That's called the hydrolysis of ester under acidic condition. And also, the oxygen in the ester group is from the alcohol. Okay, you can verify this from this mechanism. The alcohol attacks on the carbonyl carbon, and eventually this O from the ester is the same one that's in the alcohol. Some examples here. Benzoic acid, the starting material. Methanol, under acidic condition, that's our reagent. And the product should be the methyl ester of benzoic acid. We also name it as methyl benzoate. We will talk about the nomenclature in the next chapter. And another tricky question here. So in this next molecule, it has two functional groups. One is a carboxylic acid. The other is an OH. And we know OH can react with the carboxyl group, right? So under acidic condition, this molecule will have an intramolecular esterification, which means the OH in the same molecule on carbon 5 here will attack on the carbonyl carbon of the acid on carbon 1. So it's going to form a ring. And this ring will involve six atoms. 5 of them are carbons between the OH and the carboxyl. And the last atom will be the oxygen of the alcohol part. So here is the product. 6-membered ring ester. if we label the carbon atoms, it probably will be easier for you to see how the ring is constructed, right? Okay, 6-membered ring involving carbon 1 through 5 as well as the oxygen. So the final product here is a cyclic ester. We also call it lactones. Okay, so lactones are cyclic esters. The second way to form esters, especially methyl esters, we can react carboxylic acid with diazomethane, CH2N2. So, for example, if we have benzoic acid, we can deprotonate benzoic acid by reacting it with a base, which I didn't show, but we want the anion, we want the benzoate. So benzoate, the anion, can react with diazomethane by donating its electron to the negatively charged CH2 group. At the same time, the carbon-nitrogen bond will break in diazomethane, and the leaving group here will be NH2, which is the nitrogen gas, and it will escape from the reaction mixture, and that's the driving force for the whole reaction. And lastly, after acidification, when we add water to protonate the CH2 minus here, it gives the methyl ester. All right. Now, something that I do want to point out here is that in the previous Fischer esterification, we have alcohol attacking on the carbonyl of the ester. Alcohol attacking the carbonyl of the carboxylic acid. There, the carboxylic acid serves as the electrophile, accepting electrons from alcohol. Okay, so carboxylic acid in Fischer projection is the electrophile. In the reaction here, formation of methyl ester with diazomethane, we have the carboxylate ion attacking the methyl group in diazomethane. So the nucleophile is the carboxylate ion. Okay, it's the negatively charged oxygen of the carboxylate that's attacking an electrophile. Okay, so the role for the carboxylic acid or for carboxylate in these two esterification reaction will be different.